Welcome. So in this video, what we're going to do is update our beam example script in order to produce a frame, but more importantly, to add in some uniformly distributed loads. So before I get on to that, what I just wanted to do is pick up on some common issues that I've found some people are having. So I think this is perhaps because I was not completely explicit for certain components in terms of what the input should be. So really this is just to do with how we're post-processing the information, so the node displacements and beam end forces from Python, but I just wanted to run through a few of them. So this partition list component, which is taking the node displacements, for each node we have three displacements, so the X and the Y translations and then the Z rotation. So I'm just going to make really explicit the input to this partition list component. So I want that to be 3, and I will just make that a multi-line data, so we can just feed that in here, and I'll add that to the group. So add to the group. So all I'm doing is just making really explicit what I'm up to in this group, basically. So we'll just add it in there. The next one is the beam end forces. So these, we obviously have 2 nodes for each beam and 3 end forces for each node. So this partition list component down here, we want to have 6 down here. So again, I'm just going to put in a panel to make that number really clear. So we're just going to say that as multi-line data, set the value to 6, and we will add that in here. I'll just move it over and add it to the group. And then the final one, again, I should have been a bit more explicit here. So down here on this create vector component as a cross product between 2 other vectors, which is what we use to create the y-axis. This input, so the unitize input, we want to turn to true, and that basically just means that the y-axis vector will have a length of 1, and therefore all of our sort of other aspects in terms of the magnification factor, but also just the values that we're plotting for the bending moment and so on, they will scale as we would expect, rather than in a way that would basically assign that y-axis a much longer value compared to just unitizing this value. So this is a Boolean, i.e. it can have a true or a false value. So I'll just join in this component, add it to the group. So we'll just run that in there, and then I want to set that to true. So those are just 3 inputs to components that I wanted to make really clear, because I think they have been common issues for some people. Okay, so the first thing that we're actually going to do is we're going to come back here, and rather than just construct a line, I'm going to use some of the techniques from the tips and tricks video. So I want to build a frame. So initially I'm just going to do that down here. So we'll have a panel. It doesn't really matter the exact dimensions, but I'm going to have a point at the origin, a point 2 meters, so 2000 millimeters up, and then I'm going to have the next point all the way over at 4000 on the y-axis, and then again it'll be 2000 millimeters on the 2000 millimeters on the y-axis and 4000 on the x-axis, and then obviously the final one in there just down at 0. I think what I'm going to do is I'm actually just going to add another point in here because we can now deal with pitched elements, so that is elements just at an angle. So I'll put this midway across and we can just set that up like so. Turn that into multi-line data as usual, and then I'm just going to make sure they all run into a point component there. So the next component that I'm going to use is something called polyline. So that just takes all of the components in here. So these are my vertices, and then it will produce a line coming out from there. And I want to just leave this option here as the default. So I don't want to create a closed polyline. So just checking over here, this is the shape of my portal frame that I'm producing. I want to basically kind of atomize this, so get it so that rather than having a polyline, we just have one line for each structural member. So I can explode my curve like so, and again I'll leave it as the default option, so recursive, which basically just gets everything down to this kind of atomic value. And I'm going to put that output just into a curve. So these I'm going to put into a group, and I'm going to call that group build a frame in this case. So what I can do at this stage, I can actually come up here. We don't need that build a beam group anymore. So I'm just going to delete that. And then what I can do is I've got this curve here, so I can feed that into that component there. I'll just briefly zoom out, so I'm going to select everything. You don't really have to do this, but I'm just going to move it back onto the canvas like so. Okay, so we've now done our first part. So the next thing that we can think about is how do we want to give this UDL information. So that's what we'll move on to now. So we're obviously going to give it in a panel format, but this time the information that we're giving in each panel will basically be the element and then the uniformly distributed load in the X direction and the uniformly distributed load in the Y direction. And we want to have local and global options for that. Okay, so we'll put in a panel here. This we want as multi-line data, obviously. And I'm just going to add that to its own group. And I'm going to call this one local UDLs. And the format that we want in here, so it's going to be element and then WX, so that's the uniformly distributed load along the length of the element in the X direction, and then also WY, so again uniformly distributed load, but this time acting in the Y direction, so in the local axis system. So basically if we want to have a downward load, we're expecting WY rather to be negative in this case. So those are our local UDLs, and then we'll have another panel. Again, we'll just group that, and the name I'm going to give this is global UDLs this time, and this is a very similar format, so we want it element. This time I'm using the global axis, so I'm going to call that WX dash, and then WY dash is the other one there. Okay, and I'll just make that multi-line data. So we can obviously just input values directly into here. Because we know that we're likely to be applying the UDL over a series of elements, for example, something that we might want to consider doing. So I'm just going to build a little way of doing this, so we can have a series, and obviously this will be our starting element, going up in steps of 1, so that's fine, we can just leave that as it is. And this is the total number of elements that we want to apply the load onto. So in here I'm just going to have a panel, and at the moment I'll just set this to a value of 0, so I'll feed that in as my starting element. The count, so because I have split every structural member into 8 elements just as a sort of default at the moment, I'm going to count 8 on here, again changing that to multi-line data. So we'll just run that in like so. And what we can then do is use something called the concatenate component. So I'm going to run the series into A there. What I then want is I want to separate the element information from the loading information, just with a comma and a space, like so. Again, make that multi-line data. So I will run that into the next part, and then I just want to add an input there on my concatenate command, and then I'm going to have a final panel here, which is basically actually going to be my WX, WY components, and at the moment I'm just going to put in some slightly arbitrary values, but I'm going to say 0 and then minus 0.1 in here, and again I can turn this into multi-line data. Now if you did want to have several bits of uniformly distributed loading, what you could do is be quite clever just in terms of having multiple values on multiple lines in here, and then similarly here. You may just need to be a little bit careful about how data is being handled coming in here. So for example, grafting or flattening as appropriate. But what I'm going to do here is just always say that we want to flatten the data coming from that concatenate component, and then we want to basically run that into our panel. So you can see in the panel here now, this would be loading elements 0 to 7 by 0.1 Newton per millimeter in the negative Y direction for those elements. Okay, so I'm just going to call this define local UDLs, and actually we can obviously say that we want something quite similar if we were to define global UDLs. So in this case I'm just going to copy that, Control C, and then Control V, so that copies that entire group across like so. So I can now just connect this in. Obviously I don't actually want this at the moment for purpose of our example to do anything, so I'm just going to set that value to 1 there, and then I'm going to go back and set these values just both to 0. So although it's sort of imagining it's going to apply a global UDL to element 0, obviously by setting the magnitude of the distributed loads to 0, that's actually not going to add anything into our analysis, and obviously I'll just say define global UDLs there. Okay, so we've got all of the input information that we're likely to need. Now what we want to do is just create a new Python component. So there's kind of enough going on when we're creating UDLs that we probably want this as a separate component. We just need to briefly think about the information that we're going to have coming into that component. So we will have the number of nodes, the number of elements. We do also want element nodes, element length, and element angles. and then obviously the new input information that we've got, which is the local and the global UDLs. So we'll just add that now. Okay, so bringing in our Python 3 script. So in terms of the inputs, we do just need to go through and quickly set these. So some of them are obviously identical inputs as we had up on our original analysis component here. Some of them, or a couple of them, are now our new components here. So we'll just try and go through this fairly quickly. So we want the number of nodes. For 1, we want the number of elements next on there, and then we're just going to add several others here, and then we'll run through getting them set up. So we want the element nodes, we want the element lengths here, and then also in terms of inputs that we had before, finally the element angles. And then obviously the other two inputs that we want here are the local UDLs and then also the global UDLs. So I'm just going to go through. So obviously the number of nodes here, we want item access, that's fine, and that'll be an integer. Number of elements, item access again, and that is also an integer. Element nodes, so this one we want tree access on, and if I remember correctly, these are integers. Element lengths, we want list, and these will all be floats, and then element angles, again list, and also floats in there. So the local UDLs, the way we've put them together, we want list access, but we're going to be processing a string, so essentially we're just giving a bunch of text and then we're going to let the Python script to take care of it. And the same for the global UDL, so setting it to list and setting it to string as well. Now I'm going to define just a couple of outputs at this stage. So first of all, I'm going to call this one FENA. So this is the force matrix, but it's the equivalent nodal actions that we want to add. And slightly unusually, I'm going to set the type, so I want it to have no type, because this is just going to be some information that I'm taking from one Python script, so this one here that we're developing, and then I'm going to put into another Python script in a second or two. So the other one that I want is something that I'm going to call the element, or LM, and then N equivalent nodal actions rather. So for each element, this is going to be the equivalent nodal actions at its nodes. So this will be a series of 6x1 matrices basically, but it's just taking the FENA data and reprocessing it in a slightly different way. And for this, I want to also set it to no type hint. So the next thing I'm going to do, I'm just going to do the usual. I'm going to put in a bunch of relays. I'm just going to briefly turn off the bifocals just to try and make things actually slightly clearer at this stage. So just lining up these relays here, like so. Oh, I've seen one in there. Just come back and get it. Okay, and we'll just tidy that up slightly. Obviously, I could have some relays coming out here. In reality, I know I am just going to feed them directly into this component up here, but I will just add a couple of relays so that we are being consistent with how we use these. So just like so. Okay, and then I'm going to group this whole lot. So let's group like so. And I'm going to call this constructing equivalent nodal actions for UDLs. Okay, so what we're going to do next is just bring in our Python script, and then we'll connect everything up. We're going to need to make just some very minor edits to the Python script that we already have doing the analysis, but we'll then see how everything's working in just a few minutes. Okay, so I've got my equivalent nodal actions text file, only because it won't allow me to attach Python scripts to PDFs. But you can download this and open it up in Notepad, or it happens to be TextPad that I use. So in here, I'm just going to do Control A to select everything, then Control C to copy everything, come back into Grasshopper here. So I can now open up this Python component. There we go. So I'm just going to come back, delete the default in there, and then paste everything in there. So at the moment, obviously, it'll, issue an error because I haven't yet connected all of the information that I want in here. So now all we need to do is we've got a lot of this information up here on the original component. So I'm going to connect my number of nodes, number of elements, my element nodes, all from just the relays up here. So I've got my element nodes, element lengths now, and then finally element angles from up there. And then from down here, I've got my local UDL information, and then my global UDL information. So once I've got all of that connected in, you can see this is basically a happy component now. So what we now want to do, this is all well and good, in that we're getting information to these outputs, but we obviously need to do something with them. So what I want to do is I want to take these as Python. These are NumPy arrays in Python at the moment, and I need to get them back up into this analysis component up here. So to do that, I can just zoom in. So here, this is going to be my F, just getting the cases correct. So my F, ENA, and my LM ENAs are what I want to bring in here. I will just add relays in here. So C, Control V. So just bringing them in like so. I'll just move all of this add these into the group, and then finally just tidy these up fractionally. Okay, so in terms of the data types, we want this type hint So again, no type hint here. It's kind of just having the Python data and almost hiding it. We don't want Grasshopper to do anything with it, basically. So now we can run my F ENA and then LM ENA up here. So that's all good. But at the moment, it won't be doing anything with that information because the Python script in this component doesn't have what we want. So I'm just going to double click here. So all I'm doing is replacing the current Python script in here. So I'm going to say Control A, delete. Obviously, if I was to rerun this, it would kick up all sorts of issues. But I'm going to come back out, and the file that I want now is this stiffness method update 01. So in here, Control A to select everything, Control C to copy it, then back into Grasshopper, so Control V now. So you can see if you look at the length, nothing much has changed. Essentially, there's just a little bit extra going on here. So I'm subtracting the equivalent nodal actions from the force matrix. So this will now only give out the applied loads in terms of the reactions and the originally applied loads. And I'm also just making an adjustment to subtract the equivalent nodal actions from my beam end forces matrix. The final thing I've just added in is I'm going to get my reactions out. So that will include the original applied loading, but we'll just show how we can process those reactions in a second. So if I save this, we can see everything's running appropriately. It has just popped up a little error, but this is to do with an ill-conditioned matrix. So all it means probably is that the maximum stiffness that I've put in related to the boundary conditions may be causing a little issue. If you run it again and that message disappears, generally everything is still okay, so we won't worry too much about that. Okay, so from here you can see we've got all of our nodal displacements coming out and all of our beam forces, so this is all good. What I'm just going to do is if I plot my bending moment diagram, so you can now see, based on the distributed load and the boundary conditions that I haven't yet updated over here, all the point loads, this all seems quite reasonable. So I'm just going to briefly show those node numbers. So we'll zoom in a little bit. So you can see at the moment my boundary conditions were only applied to node 0. So basically quite a lot of the structure wasn't really doing anything. So what I want to update them to is I'm not going to restrict rotation. I want to add a boundary condition on the other side, so I'll make this a pin. So that is, I'm going to fix it in the X and Y directions. I'm going to alter that to 0. I'm just going to temporarily take my point load off, so I only want to see the effect of the distributed loads. So if we come back out here now, okay, so we can check our bending moment diagram. So this seems fairly reasonable. We have our UDLs here, and we can see that that is a quadratic distribution. But then where we're not applying any further loading, we go back to linear variation, and the bending moment diagram is being plotted on the tension side. So if we just have a quick look at the stress distributions, so we can see that looks quite reasonable. So we have tension on the inside initially, and then by the time we get to the other side of the portal frame, bearing in mind it's a lateral load, it makes sense that it's in tension on the outside by that stage. Okay, so one thing that we want to do is just go back and deal with the reactions. So obviously this is something that's useful to know about. So I'm just going to add reactions here. So we could process this within the Python script itself, but I think it's quite helpful to see how we can process it outside in Grasshopper. So that's what we're going to do. Obviously in terms of type, this is just a list of floats that's coming out, so we'll set to float there. I'm going to add a relay as I usually do, so we'll just add that in there and add it to the group, and then just before we go on to set everything up, I'll just do a little bit of tidying up like that. So I'm going to come up over here and I'm going to bring the numbers of the reactions just across into this component first of all. And what we can see if we look at the list of numbers, so there are some that obviously have, distinct values, and then there are quite a lot that are, minus 8, minus 10, in terms of scientific notation. So these are really very small numbers that arise out of the numerical or the computational process, and essentially we want to get rid of them so that we're left with the reactions and the applied loads, and we will also have information about the degree of freedom in the system stiffness matrix that they are associated with. So essentially we expect to see them obviously where we apply the boundary conditions or where we've applied point loads. So I'm going to use the absolute component, and then I'm going to use the greater than, and here I'm just deliberately going to put in quite a small number, but a number that should just allow me to capture all of the sort of real values, if you like, and basically just get rid of those, e to the minus 8, e to the minus 10 values. So just convert that to multi-line data there and connect in. And you can see we now have sort of true false coming out from there. So I'm going to dispatch from here. So this is my list, and I could take this from either one of those outputs. It happens I'm going to take it from the greater than or equal to output. So you can see then we have a list of reactions coming here, and what I want to do is combine them with the global degree of freedom that they relate to. To do that, there's a slightly unusual component. So it's the item index component, and if we have a list as we do over here, and then we've processed the data in that list, but we have an item coming from it, then I can connect in there. So I'm just going to turn bifocals back on here, and what you can see, so that's the item index component, and if we concatenate the results from this, so run that into there, I'm going to use a panel there, so just comma and multi-line data, will connect that into there, and then finally obviously we want the value, so we'll just connect that in like so. So now we can output all of this information to the panel like so, and something's not gone quite right here. So I've connected the wrong one, so I should have obviously connected this output A, so the numbers that are bigger than the minimum that we've set ourselves. So we'll just kind of adjust a few things around here. So what you can now see is in this panel we have the degree of freedom. So 0 and 1 relate to node 0, the x and the y forces. And then on the basis that we had 32 nodes, so 32 times 3, so 96 relates to the x direction at node 32, and 97 obviously relates to the y direction. And we can just check that these kind of make sense. So we weren't applying any load in the global y direction. So if we look at minus 50 plus 50, that comes to 0. So we have equilibrium in that direction. And then if we look at these two values, so minus 156 point something, and then minus 43 point something. So these are going to add up to minus 200. And if we go back to our loading, so we had this load in the global y direction, this will be of 0.1 newtons per millimeter, and we can go back, so that was over a 2000 millimeter length, so a total load in the positive global y direction of 200 newtons. So if we add that load to our reactions, then we also have equilibrium in the y direction. So I'll just finish that there. So we'll just group and we'll label this as finding reactions and applied forces, which just noting obviously the applied forces are any point loads that we might have there. So that's us added the UDLs in. The next thing we want to do is obviously add some internal pins. So I'll see you in the next video for that. Final thing just to say, always make sure you save. So we'll just save the current file there, and I will see you in the next video. Okay.